Hello, everyone, and welcome to the last lecture of Lean for Scientists and Engineers in summer 2024. We have gone through all the basics of how to use logic and proofs and think of those things for scientists and engineers, and how to implement these in Lean, how to write programs in Lean, and how to tie all these ideas together to write provably correct programs for scientific computing. We are now in the last lecture, where we have Tomas Scriven from Carnegie Mellon University, who is going to be showing us how Lean works, which is his project on implementing and developing scientific computing in Lean. And I'll let him take care of the rest.
So I'm going to talk about library I'm working on called Lean for scientific computing in Lean. And so let me start with a kind of motivating why I'm actually working on this. So I guess throughout the lectures here, you've heard a bunch of motivation why it's interesting to using Lean, but I think I have like a slightly different perspective on it, or slightly different motivation. So I'll kind of present my motivation, and then show you kind of what the library is capable of so far. So the question is like, why should we use Lean for scientific computing? And one sentence answer from me is that because the language of science is mathematics, and Lean can speak it. So using Lean for scientific computing and in science in general, there has to be something interesting has to come out of it. A little bit longer argument is that, okay, so what are we doing when we're doing scientific computing? We observe the world. Based on observation of the world, we formulate some mathematical theory. And then we want to make some predictions, right? So we can do all the math on the paper, but that's usually not the case for complicated and difficult scenarios. So we have to do, we first have to take the mathematical descriptions, write it in some form that we can actually implement on a computer. And I would like to point out that both of these steps is done manually on paper. Then the next step, we turn the mathematical model into some form that can be implemented in a computer. Then we have to go through the manual task of actually implementing it. And then we can let the computer to run the simulation and give us a prediction. So I would like to do this a little bit differently. So with Lean, I would like to hope that we can directly write the mathematical model on a computer, and we let the computer do the rest. Okay? And I think Lean is a great language for this because it can express all these steps. So it might be a good language for doing this. Of course, this picture is like too naive that like hope that all these steps can be done on a computer. So what I really hope is that we actually can guide the computer in all of these steps. And I think like Lean interactivity can play a crucial role in this task. So a little bit more into details. So I think like there are more like 4 main pillars why using Lean is exciting. And the first one, which is kind of unique to interactive theorem provers, is that we can work with the mathematical abstractions, like the mathematical abstractions underlying all the mathematical models or like the physical models can live as a first-class citizen in the language. And I think this is great because a big problem, at least in my experience with all the libraries for scientific computing, is the problem of composability, right? How do you mix different libraries together? They use different formats of arrays, and it's often quite a mess. So my hope is that because we can talk about the math itself, we can build interfaces for these libraries that talk only about the mathematical abstractions, and this would lead to great composability, and we can like just mix and match different libraries, right? I don't know, you probably, some of you might be familiar with Julia, and Julia has an amazing story of composability, but I think Lean can do even better because you can kind of completely forget about all the implementation details, and all the libraries can have real interface just on the mathematical level. And the next step is the interactivity, and I think like the tactic mode in Lean was originally developed to write proofs, but I think it can be utilized to do a bunch of different stuff. And one way is to do a computer algebra system. So, right, you can write an expressions, and then similarly you write a proof in a tactic mode. You can just write the command that manipulates this symbolic expression, and you can either do it with a mathematical expression, or you can take a source code and transform it. And one nice application is that you can optimize the code this way, right? So you can first write down very naive implementation, which you know that it's correct, and then you just transform it into something that is more performant. And in general, I'm really interested in this aspect where you write down the mathematical specification involving differential equations, integrals, solving some complex systems of equations, and then just interactively you turn this into something that you can implement on the computer. The next step is the extensible syntax, right? It's important that the code we write actually resembles the mathematical notation, such that it's familiar to people coming from all the different scientific fields. And the last but not least is the formal correctness. Lean is great that we can actually be sure that we can write proofs and then be sure that the program's actually doing what we wanted it to do. But with the last step, I would like to warn you that the library I'm working on, Silene, it is not a formalization project. So my primary motivation is not really the last point. It's more of these three points. And the last point is kind of nice, but it's really difficult. So I'm not really focusing on it too much. And I'm more trying to answer the question is that, okay, we have this beautiful library of formalized mathematics, MATLAB. And the question is like, okay, so what do we do with it? So I'm kind of imagining the scenario once we have all the mathematics you can imagine is formalized. I'm trying to figure out, okay, how can we help scientists to actually write better software? So loads of the stuff in Silene, like I'm warning you, is I'm just postulating the mathematics and kind of worrying about the proofs later. I'm more interested in actually how do we, once we have a library of mathematical theorems, how we can then help people to write better software with it. So let me give you now a little bit overview of the whole talk, and it will be more or less separated into 3 parts. So in the first part, I will show you example of simulating the wave equation. And this will really demonstrate the idea of, okay, we specify the problem, and then using a bunch of commands, we will turn it into something that can actually be executed on a computer. And this kind of nicely will demonstrate all the main ideas behind the whole library. And then I will have 2 kind of sections demonstrating what is actually possible to do with Silene right now. So the one will be working with arrays. So Silene has reasonable support for tensors / n-dimensional arrays and allows you to work with them, I think, in fairly nice and comprehensive way. And then one big topic I'm really interested in is symbolic and automatic differentiation. And I don't know if you're familiar, for example, with JAX in Python. The whole library is centered around function transformation, and it exactly allows you to automatic differentiation or vectorization of code. So this kind of JAX is big motivation for this part of Silene. Okay, so let's talk about the first part. So I will show you how to write a wave equation simulation. So here is a visualization of a wave. And so let me just give you a little, before I jump into the code and show you how this is done, I'll have to talk a little about differential equations, such that we are all on the same page. So lots of physical systems can be described by the second Newton's law, where the acceleration of a particle is equal to the force. One way how we can rewrite this differential equation as a system of two differential equations where we say that the position of the particle is equal to the velocity, or the derivative, the time derivative of the position is equal to the velocity, and then the time derivative of the velocity is equal to the force. Okay? And this way we kind of convert, there's like a general theorem that any differential equations of higher order can be transformed into a system of differential equation of first order, and this is exactly the thing. So the next thing is that once we have a physical system that is described purely by a potential energy, then the force is equal to the negative gradient of the potential energy. Okay? So for lots of systems, it's enough to just provide the potential energy, and once we know the potential energy and we know that this is the only kind of driving force of the system, then these equations describe the evolution of the system. This can be slightly generalized. So this is something called Hamiltonian formulation. I'm not expecting you to, like, if you're not familiar with the Hamiltonian, don't worry about it. It's not too important. But the whole idea is that someone gives you so-called Hamiltonian. This is just energy. So this term is a kinetic energy, and this term is potential energy. And if someone gives you the energy of the whole system, then you can rewrite these equations, this equation, in this form. So the time derivative, the time of position, is equal to the derivative of the Hamiltonian with respect to the momentum. So P is the momentum, which is just the mass times velocity. And the time change of momentum is the negative derivative of Hamiltonian with respect to position. So what I just want you to take away from here is that we can describe this system of a wave equation by providing this function. And then by computing these derivatives, we can obtain the evolution equations for this system. So let's go back a little bit and talk about the differential equations in general. So what is a differential equation? If someone gives us a function f, which is a function of time and a position y, and it gives us an initial time and an initial position, our task is to find y, which is a function of time, such that its time derivative is equal to this function f, and it satisfies some initial condition. Okay. So this is differential equations, and we will be interested in the differential equation for the Hamiltonian systems. So we can actually see this differential equation in this form. And we can do this by, okay, our y, the trajectory, is now a tuple of the position and the momentum. And this function f, right, is a function of t and y, but y now is the position and momentum, is just this pair of, right, the first position is the derivative of the Hamiltonian with respect to the momentum, and the second component is the derivative of the Hamiltonian with respect to this is derivative with respect to momentum, and this is derivative with respect to the position. Okay. And the last component before I can jump into the code is that in Silene I have this function ODE solve, which exactly returns the solution, the y of t, of the differential equation. So if we know the function f, which defines the differential equation, the initial time, the initial condition, the initial state, and the time where we are interested in, like, the solution, then this function returns the solution of this differential equation. Okay? And I stressed out that this function is non-computable. So in Lane you can write down non-computable functions, and this function is defined as if there exists unique solution of this differential equation, then please return this solution. And if it doesn't have a solution, then I think it returns 0 or just some junk value. So this function is really, it's using classical reasoning, and it's completely non-computable. Right? Like in other programming languages, you cannot say, like, oh, if there's a solution to some differential equation, please return it. So this function is purely non-computable. So the way I kind of think about it is, it is purely symbolic function, right? So for example, in mathematics, I can define functions that are completely purely symbolic. Doing this in Python is not so easy, but in Lean, there is not much difference between those two functions if you just want to reason about the code, not if you want to execute it. So the takeaway pieces is that there is this function ODE_solve. We need to provide this function f that defines the differential equation, and we provide the initial time and the initial state. And for physical systems, that they're called Hamiltonian systems, the particular choice of this f looks is this way, okay? Where h is a function that defines the energy of the system. So with that, I can jump. That I can jump into the link. Okay. Okay. Everything's too fine. Okay. So here I define the Hamiltonian, the energy of the system. So because it's kind of wave, then there are two constants, which is the mass and the stiffness of the wave, like a spring stiffness. And then the energy should be function of position and momentum. And because we are interested in simulating wave, then we need kind of, for every position, we need the deflection of the wave and its velocity. So this why the type of these, the position and velocity, is actually an array of n floats. And the energy, this part is the kinetic energy, which is effectively the square of the momentum. And here is the potential. I will not go into details why the energy looks this way. But yeah, so the important point is that the wave equation, if you actually discretize in space, then this is a reasonable choice of defining the energy. Okay. And now, yeah, the idea behind Silene is that you write down a specification what you want to solve, and then kind of describe how you want to turn it into something that you can actually execute. So this command is a specification of the problem we want to solve. As I said, the function ODE_solve takes a function that defines the differential equation and returns the solution. And this command is exactly saying, please define a new function called solver, which is approximation of this function. And these commands will be these will be instruction how we build approximation of this function. And and in the presentation, I said this function f should be a function that takes time, position, and momentum, and returns two values. And the values should be a derivative of the energy with respect to the momentum and the derivative of the energy with respect to position. And here is exactly that. So this is Silene's notation for derivatives. So you can, what it says is that here is please take a gradient with respect to the variable p prime and evaluate it at the position p and you're supposed to take a derivative of this expression where I say, okay, the energy, and I'm differentiating with respect to the p prime, with respect to the momentum variable. And now I'm let me finish that. And the second component should be again, right? Like now we differentiating the Hamiltonian with respect to the position. So now when we jump into these instructions, yeah, we can look at the info view, and the info view is exactly saying, so this approx is some inductive type, which I will not go into the details how it's defined. But the idea behind this inductive type is that it will hold approximation to something, and it holds approximation to this function. And right now, because this function contains the function ODE_solve, and it contains the derivatives, which are both non-computable functions, right? The derivative is defined with some limits / filters, and ODE_solve is again, right, saying like, oh, if there is a solution to the differential equation, just returning. So we want to create an approximation. This object here will actually, at the end, will store information about the parameters in which we are doing the approximation. So very often, right, for example, we turn integral into a sum, or we turn derivative into a difference where we take the difference with like a fixed distance between the values, right? So this object will at the end hold information about, for example, how many numerical steps you want to do, and it also stores the information how these parameters should be sent to infinity to obtain relative approximation. So when we want to turn this specification into implementation, we need to do two things. We need to eliminate the function ODE solve. We need to approximate it with some numerical scheme that time steps through the differential equation. And what we need to remove the derivatives. So for that, we will apply automatic differentiation. So the first step, we just unfold the definition of the energy. So it's just unfold the definition, and we see here. The next step, we run the tactic autodiff, which is Silene's implementation of automatic differentiation, and it's just written some like. There is no point in actually trying to understand this. The important thing is that all the functions here are now computable, except we still need to replace the ODE solve. And this is the next step. So in the next step, okay, so this command conf in ODE solve allows us to, we just want to focus on the expression starting with ODE solve. And we rewrite this using a theorem which says, okay, this theorem says that the function ODE solve of f is equal to a limit when we send n to infinity. And here's a function ODE solve fixed step. So effectively, this is implementation, and that provided a function that some numerical integrator like Euler method, backward Euler method, Runge-Kutta method, or something. I'll take this kind of numerical scheme, and it will time step through the differential equation. Okay, and right now, as I said, Silene. Right now, the goal is not to provide everything formal. So this theorem is just stated as it is, and there is no proof of it. But I'm kind of assuming that for this to be true, one has to kind of show that the solution, that the equation actually has a solution, and that the time stepper is actually a time stepper for is like a valid time stepper that can integrate differential equations numerically. Okay. So we rewrite this, and now we can see that if I jump in here. So now our goal is to create an approximation of a limit, and now we run the function that is the ODE solve. Maybe, yeah. Okay. And the nice thing is that this function now is executable. So there is no non-computable function in there. And the last step, I use the tactic approx limit, and the tactic approx limit, what it does is it looks for an expression that we are taking an approx of a limit, and then we kind of consume this limit into the approx object, and the approx will kind of store the information about the limit, and it will store information. Okay, we are creating an approximation of this expression, and there is this free parameter n, and we should send it into infinity. So once we call the approx limit, the limit completely disappears from this, and now we are right now our goal is to create an approximation of this expression. But this expression is like function that we can actually execute, so we don't have to do anything, and we just can stop providing. Okay. And so, for example, if I would remove the last step, then the compiler would be complaining, because it would say, okay, I cannot compile this definition because it actually depends on the function limit. Okay. So yeah, and here is an example how you can actually use the function solver. So it's just you set up some initial conditions, and then you step through the time, and you can call the function solver, and then you need to, because right, we did one approximation, And the approximation was, we sent a number of steps into infinity. We need to pick a number of sub-steps. So we kind of provided this parameter for the limiting behavior of the approximation. But yeah, this is doing some poor man's version of plotting, but because Lean has widgets, we can actually display it nicely. So you can open it up in VS Code, and just play around with it. If you click somewhere, it will create a disturbance there. Sometimes the mouse is not working for some reason. I don't know. Sometimes it just gets frozen in this position on the initial machine. So
thanks. We have some questions in the chat.
yeah, I'm just looking at it exactly. So this effectively this concludes the first part of the talk. And yeah, so what I wanted to show you, kind of demonstrate exactly. This is kind of the end goal of Silene, which is still not fully well developed. And the idea is that, yeah, how to develop a software in scientific computing is that you effectively write down the mathematical definition of the problem, and then you turn it into right. So let's look at the questions. As the function can return bogus. I see. Yeah. So the first question, as this function can return bogus, are we wrapping it in an option? No, we are not wrapping it in an option. It is similar to, for example, division. So in Lean, if you divide by 0, then it's equal to 0. If you differentiate the non-differentiable function, then it returns 0, and it's on many cases. So there is a great blog post by Kevin Buzzard about exactly that. Why do we actually define division by 0 to be 0? It's a matter of convenience. So yeah. What does this evaluates to? So check load n, right? A set. Oh, so if you don't know, if there is a notation and you don't know what it evaluates to, what you can do, you can set option, say, please turn off notation. So we can see that the float kind of to the nth power turns into data array, and data array n, it's effectively saying, please create an array that has values float, and the elements are indexed by this type. And I will talk about it in the second part of the talk. Right. So the question is more or less, how do I know when ODE solve returns junk value and when it doesn't? So right now, the thing is that Mathlib does not really have a... Okay. This really goes back to why do we define division by 0 to be 0? And how do we work with it, right? So, because for example, with real numbers, you cannot really evaluate the code, so you don't really, you cannot really actually run the function, right? So you can only kind of symbolically manipulate it. And when you symbolically manipulate division, then quite often with lots of the operations, you have to prove that the denominator, right, is non-zero. So the same way, if you would symbolically manipulate the function ODE solved, then you have to show that this differential equation has a unique solution. And that's exactly what I kind of omitted here at a sorry proof. And this sorry proof is exactly saying, okay, please, that, okay, this differential equation has unique ODE solution. And that's kind of the philosophy of Silene right now. So Mathlib has very basic theorems about differential equations. So the theory of differential equation is not well developed yet. So in Silene, I just postulate theorems that I'm mostly familiar with it, that they are correct by studying mathematics. And I'm not worried about proofs right now. So so I kind of treating that, okay, when you do this, then maybe you have to go and check all the stories and say like, okay, yeah, well, this function is most likely a differential equation defined by this function has the unique, because I think like you can probably, maybe it would not be that difficult because you can prove that this function is Lipschitz, and then maybe even MATLAB has a theorem that for Lipschitz functions, that for functions that are Lipschitz in the space, then you have a guarantee of a unique solution of ODE. Maybe you're not guaranteed. It's like a local guarantee, not a global guarantee. So there might be some issues. So I'm not right now worried about it. More, I'm kind of trying to, imagining once we have all the formalization, how we work with it. So the next question is what the approx keyword do, right? Yeah. So this approx is effectively. Let me. Oops. So this roughly turns into MK load, and then approx by dot dot dot. Right. So this command approx effectively defines a function solve, and the type of the function solve is this object approx, which here you provide the filter in which you do the approximation, and then you provide the specification of you actually want to approximate, and then you have colon equal, and effectively you write the tactic how to actually construct this approx object. Yeah, so and the last question, if there any constraint guarantee around whether the approx is reasonable approximation or something wild completely wrong. Right now, yeah, this is part of sailing that is not well developed, is more or less kind of trying to imagine the future, how we could potentially write software like this. So there is really no guarantees. So, and also the definition of approx is not completely refined. So I can maybe just show you a little bit. So the idea that approx is based on this inductive type where you have one constructor exact, where exactly if you want to approximate something and you know that you can actually evaluate it, then you can say, okay, I'm just going to evaluate it. And then the other constructor is approximation. And right now, I haven't proved anything about it, but I'm just kind of conjecturing that the construct should look like that you have some sequence of specifications. For each specification, you want to provide implementation, and you want to show somehow that you have a guarantee of some consistency and convergence. And in some sense that consistency, if all the solutions you have some sequence of specifications, right? And if you have a solutions to the sequence of specifications, then the limit of this actually satisfies the desired specifications. Then also you probably want to convergence, saying that if you exactly have a sequence of solutions of the like partial specifications, then this actually is converging to something. Yeah, and then you also need to provide approximations to all the specifications. So what I'm kind of imagining, I think like quite often, for example, consistency can be proven. I think that's relatively easy. Proving convergence, I think it's for loads of problems is completely out of the questions. And like, I don't know, I'm interested in like fluid dynamics, and in fluid dynamics, yeah, it's effectively hopeless to prove convergence on some numerical scheme, because if you would be able to do it, then you can solve millennium problem that Navier-Stokes equation has a solution. So, but quite often you can show consistency. So there's not like, if the computer is actually returning something, then it's returning you, and it's kind of, it seems to be converging to something, then it's actually returning you some sensible answer. And the last question before using set option, how do you define an option? So there is tons of, yeah. Before using set option, how do you define an option? Is option similar to a variable? No, so there is like a bunch of predefined options. It's changing options is kind of modifying behavior of Lean itself. So there are a bunch of traces. So if you're debugging something, loads of tactics, you can turn on tracing. Yeah, so these things are more or less built in. You can define your own options as well, but they're meant to kind of help you understand what's going on with Lean. Okay, so if there are no further questions, I will jump to the next part. Is it all good? So, okay, so as I said, there will be, where was it? There will be two parts. Yes. Now I will talk to you about how to work with arrays, slash tensors, and dimensional arrays. So with that, I would like to point you to direct you to. I started working on manual for sailing. I think I posted it on the Zulip. So if you go to Lean for Science Engineers class, and yeah, here, start working on the reference manual. Okay. And right now I have only one chapter, is exactly about working with arrays. So I will kind of give you a quick version of this chapter. And hopefully in the upcoming months, I will work more chapters on working with arrays or automatic differentiation. I have some experience with probabilistic programming and stuff like that. So, okay, and the way I will do it, I share the whole file, but I effectively delete all the code, and I will just live code it in front of you, and hopefully nothing goes wrong. So if you're familiar with Lean, there are two main type of arrays. One is lists, right? So and we can write list with a square bracket. So yeah, okay. So now we have a list of floats. We can also create an array. And the main difference between lists and arrays, if you I don't know, yeah, if you're familiar with programming, then you probably implemented lists because this is a linked list. And arrays is really a continuous block of memory where it stores the floats. The only trouble with Lean's arrays is that it actually does not really stores the floats itself in a block of memory. It stores a bunch of pointers into these things. So what is nice about arrays is that you have a quick access to its element. So if I ask for the first element, for example, right, or like for the second element, with lists it kind of has to go through all the elements from the start to get like to the desired element. With arrays, you can just like jump into the correct place. But the problem with arrays in Lean is that, yeah, you jump into place, but then you have a pointer and then you have to jump again. And when you do scientific computing and you do like a number crunching and you have arrays of millions of elements, having this interaction with pointer is like totally destroys the performance. So inside Lean, I have a different version of arrays, which exactly stores all the elements in one continuous block of memory. So hopefully it will be performant. So, what I wanted to show you also. So yeah, so Lean itself has more or less these two types of arrays. Then there's also in Mathlib, we can Mathlib has arrays this way, but Mathlib arrays / vectors and matrices, they are just functions. So if you create a vector of 2 elements, it's just a function from fin2 to floats. And if you create a matrix, so you can create a matrix with the double 0, 2, 3, and 4. Okay. So it says it's a matrix fin2, but I think if we actually jump into the definition of matrix, then again, matrix is just a function type. So these things not very good for computation because they actually do not store the data itself. So in Silene, I define a new version of array, and if you just want to write a short array, then you started with this symbol. The idea is that it looks like a bit of an Excel sheet where you store elements, and how you write it is slash b n plus. I don't want. Yeah, okay. So this way, I think it's shorthand for plus in a box. So you can create vectors, and yeah, it shows that the type of it is a float to the second power. You can also create a matrix. Plus the similar to the Mathlib notation. So you write a first row, then you add a semicolon, and then you write the second row of the matrix. And you can see it created a matrix with a 2 by 2. Okay, so the basic operation with arrays is we need to access the elements. Okay, so here I created a vector U and a matrix A. So you can get, for example, the first element of U. Well, I can also eval. So we can see that the first element of U is 1. Okay. Eval, and then we can look for the 0, 1 element of A, and yeah, okay. It's the first row, second column, right? And yeah, so this is the first row, so it should be 2. What is really nice about Lean, and is that it is a dependently typed language, right? So if you look at the type of A, right, it's a float to the power of 2 by 2, and so the information, the index ranges notation, range is stored in type of the. So Lean can automatically infer it. So if we write this thing function from the index, right, and we access this element, Lean can automatically infer that we actually, right, that the I should be an index of type fin2. The same way, check. If we access, then both I and J are inferred to be fin2. We can also do it this way. So I think we can just say, I don't know, some whatever symbol. And we are now accessing a matrix with a single index. But okay, so what should that be? Well, the only sensible thing is that this index is actually a tuple of indices between 0. So this way you can in some way treat matrix as a vector, which is just kind of nice. You can also write it, for example, the lambda notation in Lean supports kind of patterns in the arguments, so you can do that as well. It's no problem. Okay. And the inference type is exactly, you take a pair of indices and you return the value. How is this useful is that, right, so we can, for example, sum all the elements of U. We can, we can actually evaluate this. So when we evaluate it, yeah, well, should be 3, right? Yeah, 1 plus 2 is 3. So we can sum all the elements of the matrix. Ij. Yeah. So yeah, the sum from 1 to 4 is exactly 10. We can also do a product, and again, if you don't want to write down all the indices for example, for matrix, then we can just write one index this. And the nice thing about this, right, is that this is actually independent completely of the rank. So if A would be a tensor of rank 4 or something, right? We don't have to write I, J, K, L, and then I, J, K, L, right? We can just write this thing. So this kind of allows you to write code that is completely independent of the rank of the tensor slash array. Yeah, the question, how do you write more than 2D? So right now you cannot, if you want to write down like a list, like write down explicit thing, you cannot do that right now. It's just I haven't done the notation expansion for that, but I am just about to show you how to how to create tensors, how to create tensors of higher rank. So similar to a lambda notation, right? Where you effectively create a function from the from the index to the value. We can create array this way. So this is somewhat similar to list comprehension, for example, in Python. So instead of fun, you use this plus in a box, and then you treat it the same way as a function. Right? So I specify I want my index to be an element of fin4, so it runs from 0 to 3 inclusive, and then I take the index and I just convert it. I want the array of floats. Okay. So if we check the type, we see that this is a float. This is an array of 4 floats, and when you evaluate it, we can exactly we exactly see that the elements of the array are exactly the values of the indices. So nothing is stopping us to add more arguments. So float, and for example, we multiply this by 4. So if we look at the type, so now we have a matrix 4 by 4, and there's literally nothing stopping us again. So we can add one more plus 8 times k1 float. Okay, so now we have a float. Now we have an array which is 4 by 4 by 4. Just to send the message plus 16 times to float. Like here you can write whatever values you want the array to contain, right? So yeah, now it's 4 by 4 by 4 by 4, and you can evaluate it. And right now, so when you evaluate it, it just linearizes the whole array, and it pretends it's just a vector, which is one thing I need to fix. But so when you evaluate it, you cannot really see the information about the rank itself. But yeah, it kind of created 88 elements. Yeah. And I wanted to, okay, lambda notation for matrices. That was here. So one thing to look out for. So with the normal lambda notation, if you write this thing, or if you write fin4. Okay, so writing this with the normal lambda notation or this is identical. It doesn't change anything. But with the array notation, this makes a difference. So if you look at, right, so the original thing was, so there is a difference between these two notations. So this one creates a matrix which is 4 by 4. Okay, the type is the matrix 4 by 4. If you do it nested way, then you create an array of length 4 where each individual element are arrays of length 4. Okay, so that's maybe just one thing to keep in mind. Okay, so this notation is probably kind of similar, somewhat similar to less comprehensions you are familiar from I don't know, for example, Python. But it should not be the only way how you can actually create arrays. So I'll show you a way how you can create an array instead of like standard imperative style programming. So we can define array 1, and if you want to run imperative code, then you should start with this. I'm not going to explain why. If you want to write imperative style code, you just have to write id.run/do, and then you can introduce mutable variables. So I'm gonna introduce a new mutable array of size 4, and I'm gonna return it. Okay, it's mutable. I want to actually initialize it to some values, so we can just write a simple for loop. So I say that the index I is 2. So here I'm writing a for loop where I should run over all the elements of the type fin4. And what I want to do, I just want to take I and assign it to I.1. What's going on? Okay. So you can create arrays this way as well, and you can write kind of imperative style code as you are familiar from other programming languages. Even in it's currently proving properties of a code written this way is not easy. It's possible, but it's really not ergonomic. So I know that there are some people working on improving this, but yeah. So if you want to prove stuff, there are different ways how to write it. But if you're just interested in writing programs, then like, yeah, this is totally fine way of doing things. So one thing you might be not familiar is with this. If you're familiar with Lean itself, then you might be expecting me to write this thing from 0 to 4. I think this way, yeah. So this is kind of so specifying the index this way is a Silene specific way. This is the standard notation for a range going from 0 to 3. But the trouble is that now, so here, if you hover over I, we can see that the type of it is fin4, and because we now also have the information about like the bounds, we can easily access the array X. But now it kind of complains that, yeah, I guess, well, what it complains about. Yeah, here it kind of complains that you cannot really index the type float of size 4 with the type n. So what you would have to do, you actually need to convert the index to fin4. So so let I like fin4 how did I do that? Simple. Yes. Right. So you kind of have to manually take the index, which is a natural number, turn it into fin4, and then you can access the array. So yeah, this is somewhat cumbersome. So when you're working with the Silence arrays, I would recommend just using the function full range and then the index type you're running over. So let me just copy this. Of course, you don't have to do it with arrays. We can, oops. They do, yeah. You can create a matrix the same way. So here again, I want to do a mutable, like I want to initialize the matrix A in like with imperative style code. So I start with the id.run2. I initialize a mutable matrix, initialize it at 0. And then I run over all the indices, like 4x4 or 4x4. And now, yeah, exactly. So you have index I and j. They're both of type fin4. And I just assign to the so you can check that it actually gives you what you would expect. So the next thing I want to show is that, yeah, so now we will implement a function accepting these arrays. So let's define a dot product. So the function dot product, right? It takes two vectors and returns sum over I x I. So this is a dot product of two vectors, and we can also implement, for example, a matrix multiplication. So we'll have a matrix with the dimension n and m. Net load n and m. And the vector we want to multiply it with, load. And yeah. So, and we want to, right? So we want to multiply a vector of size n with a matrix n by n. So we want to, right? The result will be a vector of size n. So we use this notation to create a vector, and we sum over all j's. I, j. So we can, for example, see that, for example, here I gets automatically inverted to be fin of n, and then the return type of the mathmul function is again automatically inverted to be a vector of size n. So we can test this function. So for example, we can evaluate the dot product of the vector u with itself. We get 5, right? So which is 1 times 1 plus 2, 2 by 2. We can also multiply. We can multiply the vector u by the matrix A. Gives us an answer. The nice thing is, right, if we would like to evaluate, if you take the dot product of u and a, so maybe I just write check. This, I cannot spell check. Okay. So now I want to write the dot product between the vector and the matrix, and it exactly tells me, it's like, no, you can't do that because the argument a is just a matrix, but it's expected to be at the vector. Or if you try, for example, multiply matrix with matrix, but because it was designed to be a multiplication between vector matrix and a vector, then again it tells me that, like, yeah, you're giving it a matrix, but it's affecting a vector. So one thing is, so the way I wrote these is not ideal, because you might want to take a dot product between, like, with the matrix itself, right? You can also define a dot product between matrices, or right, or dot product between any rank tensors, right? And what you effectively do, you just go over all the elements and you multiply the corresponding elements together and you sum the whole thing together. Okay? So right now, the way I wrote this function dot, it accepts only vectors. So I'm going to show you how to actually implement this function such that it can accept arbitrary tensor. So So let's talk about general indices for arrays. Let me just uncomment the commands that failed. So I already talked about it. Let me first a little bit say what the notation float to the NM actually stands for. So float on the NM. So this is yes. Okay. So why is it all blue? Is this ASCII art messing it up? Okay, yeah, let's get rid of the ASCII art. So, okay, so what is the notation? Let's go back and let's explain a little bit what this notation means. Okay, so this notation stands for data array, and data array n of float says, okay, this is an array which stores values float, and the elements are indexed by this type. So if we have just a vector, then it's indexed just by a simple n. And what you can also do, instead of writing a single number, like number here, you can write the type itself. Okay. Why is this interesting? Is that now we are not actually constrained indexing by some product, right? So a normal tensor is that effectively you can think about it as an array which is indexed by some product of a bunch of fins, where each fin kind of tells you each particular, like the size of the particular dimension. Okay, but you don't have to do that. So okay, so I said we can, for example, okay, so this is a matrix which is 2 by 3 matrix. Okay, but we can actually we can use a different, right? We can create an array which is indexed by either index which goes from, which is like size 2, or index which is size 3. So the dimension of this is, right, so either it has 2 elements or is 3 elements. So the total size of this is 5 elements. So I think if I, for example, evaluate 0 of this type, then you can see that it has 5 elements. And you can go wild. So what was the other example I have? So I can use this, and then, for example, I can set IIC minus 2. Yeah. So now what I create an array which is indexed. So the first component of the index is either a number which goes from 0 to 1 or a number which goes from 0 to 2. And the second component of the index is an integer which goes from -2 to 2 inclusive. And the interesting thing is that quite often the dimension, the indices of a matrix, right, they have inherent meaning. And if you index arrays always from a number, from like some number 0 to some number n, right, this meaning is completely lost. And writing code with that is, you always have to kind of, you have some meaning of index, and then you have to convert it into this number from 0 to n, and then when you actually want to use the index, you have to like recover the meaning of the index. So if you actually allow arrays to be indexed by arbitrary type, that's like the requirement that this type is effectively finite, and you can somehow iterate over it, then you can maintain the meaning of the indices, and then it's much easier to write some complicated code. So, and so let me talk about, like, okay, so this type, it somehow needs to be finite and need to be somehow able to iterate over it. So And this is captured in the class index type. So if you are familiar, so index type is if you're familiar with Mathlib, then there is a type class called fintype, and index type is very similar to fintype. And there's also, I think, finenum in Mathlib, which is even more familiar with index type. The only trouble is that Mathlib doesn't really care about the implementation, so some of the implementations would lead to very bad code. So that's why Silene provides its own index type, and it has faster implementation for loads of the stuff. So you can check, for example, this is fintype, and then this kind of complicated type has also this instance. And the most important thing is that there is this function index type to fin, and this function allows you to take this arbitrary index, which has some nice meaning, and it turns it into fin type. And this effectively takes the array and linearizes into a linear memory. So let me just copy this. Oops. Right. So I can take index of type fin5 cross fin5 with the values 2, 3, and 1. And by calling the function toFin, it turns it into a single integer, and it effectively runs this computation. It takes the first component, multiplies it by 5 to the power of 0, then takes 3 multiplied by 5 to the first power, and then the last index and multiplied by 5 to the second power, and you obtain 42. Let's type these things. So here are examples how you can create. So here we're using the lambda notation for like the less comprehension, particularly, right, with these more complicated indices. So I can create a vector which is exactly indexed by indices from -2 to 2, and I just take this the integer and convert it to float. And as you would expect, I create a vector which has values -2, -1, 0, 1, and 2, which exactly corresponds to the index. If I index the array with the sum type, right, then I can do a case match on the index type, and then if it's of fin type, then I just turn it into float, and then if it's fin2, then I turn it into float, and if it's fin3, then I turn it into float but multiply by 100. So we can see that the first two values is 0 and 1, and then the next 3 values are exactly the index multiplied by 100. Yeah, you can do the sub. Yeah, you can do more complicated with more complicated. So now we understand. So like, okay, so why I was talking about these general indices is that originally the issue was that we could not run this function dot on matrices. And effectively, the issue was that all the arrays, these two arrays, were indexed here by fin n. And we would like to turn this function and index it by arbitrary type. So if we take this function dot, let's just add a dash. And we want to generalize it to arbitrary type. So we introduce a new type. We require that this type satisfies the properties of the index type. And now we take two arrays which are indexed by this arbitrary type I. And yeah, the implementation, we sum over all the indices and we do the same thing. So yeah, there is no problem. And we can do the same thing with the matrix multiplication. The matrix multiplication, and here we introduce two types. I and j, we require, oh, I need to add apostrophe. We require that both of these types, again, are these abstract index types. Then this matrix is indexed by I and j, and the vector we are multiplying it is indexed by this type j. Okay. So why is this useful? So now we can evaluate dot again. We can take a dot product of the vectors, but because we generalize this, we can now take a dot product of matrices as well. Okay. And so to test the capabilities of these two new functions, we will introduce a rank 3 tensor. Let's define t plus of I, j, k. So I will introduce a tensor that is 2 by 2 by 2. And what value do we return? Okay, let's copy this. Okay, so now we have, let me just do check. Right, see, now we have a tensor which is 2 by 2 by 2. We can again evaluate dot, this generalized dot, eval. So again, yeah, the new dot does not care about the rank of the arrays. And the cool thing is that we can multiply this rank 3 tensor with the matrix. Yeah, so we can evaluate matrix multiply a x, because the thing is we can, so the t is a rank 3 tensor, but we can actually think about as a rank 2 tensor. So yeah, t has a type, this type, which is a array indexed by fin n cross fin n cross fin n. But we can think about it as a matrix, which the first index is fin n, and the second index is this couple of index. And then now a matrix A can be understood as a matrix, but it can be also understood as a vector, which is just indexed by a pair of indices. Therefore, now this in some way is a matrix, and this in some way is a vector, and we can just matrix multiply them. So you can kind of see, if you work with these completely generalized matrix indices, then like loads of stuff kind of naturally generalizes. Let me see. Yeah, what I wanted to show you is, again, one way how we can define. So, right, one way to define the matrix multiplication was with this lambda notation for arrays, but we can the same way write imperative style code again. So should maybe introduce type index type I, index type j. Yeah. Right. So alternative definition of the matrix multiplication is that we take the matrix, we take the vector with generalized indices, and we want to create output vector which has the size I, and now we just run 2 for loops. We run once over I and once over j, and then yeah, it's effectively we just writing down this sum, and we have to loop over all the indices I. And yeah, and we can use this new definition, and we can see that yeah, the result of multiplying the t and a is 38, 48, and the previous definition, yeah, gives us the same answer. Right. So this was, I think this concludes my second part of the talk, showing you how Insiline can work with arbitrary arrays. Right. So yeah, I think this now would be, before I jump into the automatic differentiation part, I think this would be a great place to have more, to accept more questions. And to remind you again, if you want to know more how well, like arrays are used in Silene, then yeah, I would direct you to the so far right now it's still a bit rough, but I hope it's readable. And if you give me some feedback on the text, then it would be great. So I have one question: why does the type of INJ not need to be specified in mathmul --? So if you're familiar with this command variable, this command variable allows you to introduce arguments, like function arguments, kind of globally, and then every function in the kind of subsequent code, if it's using these variables, then they are kind of included in as input arguments to this function. So, right. So if I would remove this, command, then I think it complains now. Yeah. It complains because it somehow tried to automatically infer that I and j are actually natural numbers, which is not good. So now it's kind of confused by this command. So yeah, you have to use variable, and then you can see that if you look at the type of mathmul --, then these arguments are included. Yeah. Is there any interest from Lean/Mathlib folks to incorporate your arrays into Lean, making it not just Silene specific? So I don't know. I didn't talk about it probably with people too much. So yeah, I don't know if there's interest. I think like, so the for example, the data array thing. So this data array and type. It's definitely not verified. It's doing some hackery on the byte level, because if we actually look at the definition of this thing, so the data array and if you just is entire data array, so inside it's just byte array with just some guarantees on the size. And then to actually write into this byte array in and out, I'm doing some, I think probably at some places, maybe even some, if you would look at it strictly, then maybe some inconsistent stuff. Yeah, I'm just doing some hackery, which probably needs to be hidden behind like function for an interface. And I can imagine once the work on the new compiler resumes that this might be done completely differently. So I don't think it's a good fit right now, porting this to Lean/Mathlib. I'm not sure though, like the notation, right? The notation I introduce here and stuff can be completely independent of the actual data array. And yeah, that might be worth thinking about, whether this would make sense to port into Lean or Mathlib. I was talking a little bit to James about, so there is this library lean calls GitHub, which I think I incorporated some of the notation into this library. There are some issues with, I would like to use this library right now. Silene does not use it. There are some issues with universe levels. Yeah, this needs more discussions about like the design decisions. If I've done any tests, how much faster my arrays are to regular arrays and lists. Yeah, yeah, I'm motivated that I'm using data array because Lean's array is just an array of pointers, and that's bad. Yeah, the thing is that I haven't done any rigorous performance testing, so yeah, this is to be, that's future work. I'm kind of doing it and hoping that the compiler does the right thing, and once the compiler does the right thing, that I know that it will be faster, but I'm not sure if this is the case right now. If there are no more questions, then I will jump into the automatic differentiation part. ASCII art is destroying once again. Okay. Okay, it seems there are no more questions. Okay, let's jump into the automatic differentiation. So big part of yeah, when you formalize when you do physics, then like physics, half of the physics is just working with differentiating stuff, writing differential equations. So if Silene has to be a good library for scientific computing, then it needs to have a good support for simple differentiation. And now all the craze about AI, all the machine learning libraries, right? They're built on top of some automatic differentiation engine. So I need support for automatic differentiation in Silene as well. So that's kind of the motivation why I'm interested in this. And so mathlib defines. There is one more question. Can we have pointer store in Lean array to point to an integer index and access the integer through the pointer? Can we pointer store? Like if you want to store effectively pointers, then you can just use the standard. You can use the standard array. So for example, if you do array of int, then effectively what's happening on the kind of on the C level is that you have block of memory that stores pointers, and these pointers point somewhere to a memory where you store integer. Okay, back to differentiation. So mathlib defines the function f derivative. Check. So this function f derivative, there is a bunch of nonsense, and then it takes a function, and at some point it returns like the linear approximation of this function, which is the derivative. So to give you a concrete example, for example, if we take x, yeah. So we can take a derivative. You always have to specify over what field. So you can also take a derivative over complex numbers, but right now we'll work purely over real numbers. So yeah, we want to take a derivative of a function which takes x and returns x times x. And we would like to evaluate this derivative at point x0, and because f derivative is effectively a directional derivative, so we want to do it in a direction of 1. Okay. So if you check, okay. Oh, it's already, oh, damn it. So, right, yeah. So, okay. So we have the derivative, it should be a real number. And so what Silene provides, you can take this expression, then rewrite by, and then write a tactic. So what it does is that the rewrite by is a macro, which takes a term and takes a tactic and rewrites the term with the tactic. So if you like before the autodiff, you see that we are working with this term f derivative of this function, and after autodiff, oh, let me turn on the notation again. Once we differentiate this, we get just x0 plus x0, okay? Which is exactly 2 times x0, that's exactly what we expect, right? If we differentiate x squared, we get 2 times x. So I'm not a big fan of writing f derivative and then specifying r everywhere, and because it does not look very pretty. So in Silene, I've developed a notation for like kind of more familiar notation for derivatives. And because I don't write this r everywhere and specify yes, every single time that I'm working like over the field of real numbers, then there is a command set default scalar. And once we use this, then all the subsequent commands will know that, yeah, if you're kind of expecting that you should specify the field, then the field will be that the R will be used as the so, and with this you can, so writing this derivative in the new notation, we can do it this way, x times x. Okay, so this notation is saying, please differentiate with respect to the variable x, and then evaluate the derivative at the point x0, and differentiate the expression x times x. And it also knows that because this variable is just a real number, you don't have to specify this one, because it just does it automatically. Right. And now if you actually want to get what the derivative is, then again, we just run the autodiff. So now our goal is, okay, we want to differentiate x times x with respect to x and evaluate it as x0. And when we run autodiff, we get x0 plus x0. So what are the, I want to show more complicated expressions. So for example, quick question. Yeah, if I replace x times x with x squared. Yes, it works. And in this case, it already knows that it's supposed to like put the stuff together. So it's like 2 times x. So what were the examples I want to show? Let's see. Can do, for example, x squared plus x2. I think I have to put brackets this way. Is it going to work? Yes. Okay. So right now we can do, we want to differentiate with respect to x, which we do not actually have to specify that we want to evaluate at some point. We can just specify, okay, this x is of type real numbers, and we want to differentiate x to the third power plus x cubed plus x squared. And we run autodiff. Yeah, we exactly get what we would expect. Yeah, 3 times 2 squared and plus 2 times x. So I can just, yeah, all simp. Okay. Another, yeah, the alternative, yeah, you can specify this way at what point you actually want to evaluate it. So now, yeah, it will just evaluate it at x0. You can also, of course, you can use more complicated functions. So I can write sine x plus x plus cosine x, whatnot. And there is something weird going on. Okay, I don't know. Maybe I wrote incorrect rule for differentiate cosine. So yeah, right, when we differentiate sine and exponential, then the result is cosine and exponential. Derivative of exponential is just exponential. We can also, yeah, speak to it. Let's see. Oh yeah. So we can also, another example would be involving sums. So for example, we do sum over 10 elements, and we do, for example, sine of x to the I, and then rewrite by autodiff. Okay, so now, yeah, so we are differentiating this expression where we sum overall, sum from 0 to 9 of sine x to the ith power, and then we differentiate it. yeah, we can see that now. Yeah, so the derivative exactly. The exponent drops down with the exponent drops down. We get the derivative, right, which is x to the I minus 1, and then the derivative of sine is a cosine. Oh, there's a question if this is actually verified. Almost. So when you're working with the normal derivative, the f derivative, I think I am missing proof of, I think, 3 lemmas. I think two theorems are involving division, and one is involving differentiation of function. And it's effectively, I was just too lazy to look up the corresponding mathlib theorems that is supposed to be used. So if someone is interested to make a relatively easy pull request to Silene, then I can point you to, I think, like four theorems that needs to be filled in, and then the basic version of forward mode automatic differentiation is completely verified down to the axioms. Lots of the stuff involving arrays. So, like, for example, lots of the stuff involving arrays is not verified. So if you would differentiate stuff involving arrays, then it would not. But just basic arithmetic operations, then that would be completely verified. Okay, so right, so now, yeah, I differentiate some. So next interesting thing, we can actually differentiate with respect to vectors and matrices. So now I just introduce a bunch of variables. So I introduce matrix A and also kind of mathlib style matrix. So it's just a function from the index types to real numbers. And I introduce, yeah, some matrices and some vectors. So what are the exact? Okay, so partial derivative, and we'll differentiate with respect to the vector u in the direction of u at point u and direction du. And let's differentiate matrix multiplication. So ij times u j. So yeah, so this expression is exactly matrix vector multiplication, and we want to differentiate with respect to the vector itself. Rewrite onto diff. So yeah, one thing why I always write simp. So autodiff is designed to differentiate programs. So it's very careful about where it places lead bindings so that you get efficient code. But right now we are interested only in symbolic differentiation. So that's why I actually run simp, and simp completely destroys all the lead bindings, and you can kind of end up with expressions which are more readable. So so yeah, and because matrix multiplication is linear function in the vector, then when you differentiate it, you just replace the vector by the direction you're differentiating with. So again, once you differentiate, we get matrix vector multiplication, but we are now multiplying the direction we are differentiating in by the matrix. We can differentiate matrix vector multiplication with respect to the matrix also. So now and the same way, the matrix vector multiplication is a linear function in the matrix as well. So we just replace the matrix by the direction. To differentiate, we can also we can actually differentiate with respect to both the matrix and the vector at the same time. So this you would write it this way. And we have to mark both of these. Okay, so yeah, we are differentiating with respect to the I prime and u prime, and we multiply these, and then we also provide at what point and in what direction. And now, because we are effectively we're doing multiplication, so we need to apply the Leibniz rule. So we get a sum of two terms, and in one term we differentiate the vector, and in the other term we differentiate the matrix. What I want to show next thing, yeah, that I want to show that this thing. So here I did the differentiation, right, with respect to mathlib style vectors and matrices. We can do it with the same way with differentiate with respect to Silene's matrix and vectors and matrices. So now, right, I introduced two matrices. So now, because we will be working with arrays and vectors over floats, so now we kind of, this is again where the idea that Silene is not completely formal, that, right, we now effectively working over the field of floats, which is not really a field, but we just like close our eyes and pretend that floats effectively form a field. And we can differentiate it, right, with respect to floats, which mathematically, like, if you would really write down the definition, it doesn't make sense. So, right, so I introduce, again, n by n matrix and a bunch of vectors, and now I can, again, differentiate the matrix vector multiplication. So, yeah, we see, okay, we are different matrix vector multiplication with respect to the vector. Yeah, and again, now we just replace the vector by the direction in which we differentiate. And the same way, when we differentiate with respect to the matrix, yeah, just replace the matrix by the direction. Okay, let me see. Yeah, so yeah, I think this is, so I think I'm running a bit out of time. I'm not sure if I will be able to show everything what I wanted to show you. So I will pick and choose, but I think this is interesting. So I will show you, so not always we work with, so far I showed you differentiation of functions that are differentiable everywhere, but this is not always the case, right? Once we have a division, once we work with logarithms and stuff, then those functions are not differentiable everywhere, and we need to be careful about it. Okay? So, okay, let's try to differentiate simple expression involving division. So let's differentiate with respect to x at x0, and let's differentiate exp divided by exp. Rewrite by autodiff. Okay. So now, okay, so we're differentiating x of x divided by x with respect to x, and when we call autodiff, it does nothing. Okay. Right, it nothing happens, so we need to figure out what's going on. So set option. So again, here is the option. So there is this. So there's this option. It's called funtrans. Yeah, maybe I should replace it with autodiff. So there is I have implemented like a general function transformation tactic, and the automatic differentiation is built on top of that. That's why I'm setting kind of tracing of the tactic function transformation, but maybe I should replace it to autodiff. But anyway, this, if we set this option, it will give us information about what's actually going on inside of the autodiff tactic. And let's see. Oh, I'm not used to. Here we go. Yes. Okay, so we can see that, okay, it's the tactic tried to differentiate this expression, but the x kind of indicates that it did not really succeed. It says, okay, I see that you actually effectively differentiate division. So hey, here is a theorem. Here is a theorem that we would like to use. And then it tries, yeah, here it tries applying this theorem about division. And now it's telling me, or it says if failed discharge hypothesis, the x0 is not equal to 0. Oh, that makes sense, right? You cannot divide by zeros. So if you're actually differentiating division, then you have to show that at the point you are differentiating, right, you are not actually dividing by 0, right? Because at that point, this function would not be differentiable. So how do we do that? So how do we can introduce into a context effectively assumption that the x0 is not 0. We can run this again. So we run this command again, and nothing happens again. That's no good, because we actually have to say how it's supposed to discharge subgoals. So we can say, in this simple case, apply h. Okay. So the autodiff has a bunch of rules how it can differentiate through expressions, and some of the rules can have additional assumptions. For example, when you differentiate through division, you have to show that the denominator is not 0. Okay, and satisfying these assumptions is something called, you have to kind of discharge these assumptions, and you can do it by providing a discharger. If you're familiar with the simplifier in Lean, then it's the same case in here. So this is effectively inspired how simplifier in Lean works. And we can see, and we can provide that, okay, run autodiff, and if there are any assumptions, like additional assumptions, then try to close them, like satisfy them by applying this assumption that x0 is not equal to 0. And we can actually click in front of the function apply, and the info view shows us, like, this is the sub goal that we are supposed to show that x0 is not equal to 0, and we can just apply 0. And now if you look at the result, I'll simp again. So exactly, right? This is kind of the result what you would expect if you differentiate the division, right? You put the denominator, you kind of square it, and then you treat effectively, and then you treat the rest as like differentiation of multiplication. Okay, so so that's the result you would expect. There are few variants. This is not, I don't think it's important. I think maybe I show you what I want to show you. A few variants. So we do the same task, but we divide by x times x. If we divide x times by x, then we can see that the automatic differentiation tactic again does nothing. It's not replacing the derivative. And the issue is that, okay, now if you look at what the discharge is supposed to say, it's supposed to prove that x0 times x0 is not 0. But what we are doing, we are applying h, which is not exactly the same thing, right? So this is no good. We have to use more powerful tactics. So, for example, the very, very powerful tactic ASOP, which is actually capable of proving. So now when we differentiate it, right, then we get the result we would expect. Okay. And so I think one common thing I do is that, for example, imagine even more complicated scenario. Oops, x squared minus 3 times x plus 1. Okay, so imagine like now I'm dividing by some complicated polynomial, right? So autodiff is not doing anything, so I'm not happy about that. So I can discharge by, for example, saying that story of for all x not equal 0. Right, so I can do this nasty trick where I say, okay, run automatic differentiation, and And if you, anytime you have a goal in form of that something is not equal 0, just apply sorry to it. So if, and now we can see that the automatic differentiation, where is the result? Okay, yeah. So the result of the differentiation now, right, when we apply sorry as a discharger, then it gives me the expression I want. And what you can, for example, do, you can write here trace state. Let me uncomment this thing. And each time the discharger kind of sees something, you can then look at the info view and then, for example, see, oh, the automatic differentiation actually encountered this side condition. And it looks like that this is the only side condition that kind of encountered. So you can then go and refine your assumption, add into a context that this is true. And you can remove this whole bogus discharger that you sorry and do apply h prime. Right? And now we compute the derivative and we kind of refined what the exact assumption for this to be correct. So let me see. I definitely don't have time to go through everything which I wanted. So let me just go over the rest of the file and just give you a quick overview so that you can go over it yourself. Right. So far I talked only about normal derivative, but especially in physics or optimization, quite often you're interested in computed gradient. So when you compute the gradient, is that, where is this? Is a gradient, right? For example, yeah, you would like to compute a gradient. You've seen it in the wave equation simulation example, right? So for example, I have a function that takes a squared norm of a vector, and you want to take a gradient of this thing. And the gradient of this thing is the vector itself, or like 2 times the vector. Right? So this is slightly different than because this is just a directional derivative. The gradient like kind of computes the direction of the, like, yeah, if you have a loss function, right, you want to figure out the direction in which the function kind of decreases the most. So that's when you use a gradient. So here I was just giving a bunch of examples of gradients. Then when you want to differentiate code, you need a forward and reverse mode derivative, which kind of corresponds exactly to gradient and the directional derivative. So for that, there is this function called forward FVD f derivative and reverse f derivative, which corresponds to the forward mode and reverse mode automatic differentiation. There is again a notation where you use the symbol partial, and either you add arrow forward or arrow backwards. And yeah, here is just one example, right? So for example, I have a program that computes, it computes the second power, third power, fourth power, fifth power, right? You compute the derivative of it, and then we can inspect the resulting program, and again, it computes the second, third, fourth power, and then it also computes the derivatives in the same order. So here you can see again, it computes the second, third, fourth in that order. It's doing in the kind of computing the value and the derivative in the same order. But the reverse mode automatic differentiation is doing it the opposite way. So you can see that here's the forward pass, which just runs the original program, and then it runs the program in reverse direction, and it computes the derivatives. So here you first compute the fourth power, then third power, and second power. Then one more thing, yeah, here I wanted to show you that, yeah, if you define your own function, function foo x times exponential of x, and you run automatic differentiation on this, then by default the autodiff tactic cannot see through your definitions. So you would have to manually unfold the definition and then run automatic differentiation. Or alternatively, you can add new theorems and definitions into the environment, and there are macros for this. So you can define a new function transformation. You say, okay, I want to define a new function transformation, which is the f derivative of foo. And here you provide how you're supposed to, how you're gonna compute the derivative. And this command then automatically adds a new definition, which is a function that computes the derivative, and it adds a new rule, like new derivative rule, saying that the derivative of the function foo is equal to the new definition. And you can do that same thing for forward and the reverse mode automatic differentiation. So yeah, if you want to use Silene's differentiation capabilities and you want to have your own functions, then you need to call these commands to kind of create a new theorems for your own defined function into the environment. So maybe at some point I will have some special notation for definition where you just, I don't know, you write a prime here and then it will automatically generate all the differentiation rules. But right now you have to kind of manually call these commands. And you can also call a command that, what is this? Yeah, define function proposition or like function property, and you can say, oh, please create a theorem that's saying that this function foo is differentiable, and here you provide, yeah, just call the unfold the definition and run the fun prop tactic to this thing. The last thing which I wanted to show you, I'll just run through it, is that here's a. So one of the core pieces of Silene is this function transformation idea, and if you're familiar with JAX, then that's exactly. So JAX is this general Python framework for mainly used for machine learning, and exactly, it's some framework for function transformation, and you can do automatic differentiation with it, but you can do, for example, code vectorization. So you write your code over like with the single numbers, and then you vectorize the code such that you can like parallelize it and run it more efficiently. So Silene provides capability of defining new function transformations. So here I just showed, kind of demonstrated how you can easily set up new function transformation. So you can, here I just define my own derivative. I mark it with the attribute function transformation. Then what you have to do, you have to provide few lambda calculus rules. So for example, how do you transform identity function? How do you transform constant function? And how do you transform composition of functions? You provide the rules for this. And then for each individual function, so for example, here for addition, right? You provide a rule how addition should be transformed or how multiplication should be transformed. So this is kind of like extremely basic and simple setup for symbolic differentiation. Right? Yeah. So you define derivative, bunch of lambda calculus rules, and the rules for the operations themselves, and then you can use the tactic fun trans to do this function transformation. So here, this newly defined derivative, right? We want to differentiate this symbolic expression. So we can just use fun trans and it computes the derivative. So, and you can, yeah. So hopefully it should be very easy to define new function transformation, and half of, if not more than half of Silene is effectively defining new function transformations and writing down the rules. There is some art to writing the rules like such that they work well. So there's a lot more to talk about. Yeah, so this was like yeah, because I ran out of time. I don't have experience giving 2-hour lectures, so this was more or less what I wanted to show you. So let's have a look at there are a few more few more questions. Do you have a tactic that's roughly the same as other but emits side goals in the tactic mode? Do I have a tactic that roughly that does roughly the same as authorif but emits side goals in the tactic mode? Not really. I think you can probably. I'm thinking about effectively providing a specialized discharger, that you provide a discharger to autodiff, and this discharger will effectively spew all the side goals such that will create all the side goals such that autodiff will kind of run as one would expect, and then it will be the user's duty to go over all the side goals and kind of prove them later on. So, but yeah, I don't have that. The next question, I think I've seen that simp and funprop can also do simple differentiation. Can you say something about the difference between them and autodiff? So autodiff is effectively simp that is running funprop. So there are few. Yeah, there are few. For a very long time when I was working on Silene, I was using simp, and I even didn't have funprop. I was using the tape. I was abusing the type class system to actually proving differentiability. So simp in the basic form is the autodiff is simp. The trouble is that, for example, the composition rule, the way simplifier works, it does not like rules as this composition rule, because if you see a complicated expression, then splitting it into composition of two functions has many solutions, right? So I don't know if I would fun x, right? Exp. If you write function like this, right, then you can decompose it in many different ways as a composition of two functions, and the ways this is called something like a unification problem, and there is some default algorithm that works, and it does not work perfectly for automatic differentiation. So yeah, so effectively autodiff is a simplifier which has a custom simproc in it, which each time it sees expression of derivative of something, it effectively has custom rules how to apply composition rule. And yeah, so that's in a short. Well, if you I can maybe even right. So if we go to the definition autodiff, so if we go to the autodiff, then autodiff runs this funtrans tactic. Oh, okay, I'm not sure. Okay, no, I can't show this. Yeah, autodiff is just a simplifier with a couple layers on top of it. Okay, I think I've run out of time. A few more questions, or feel free. Thank you for your attention, and feel free. Maybe, what did I have? I think I had the last slide. It's just a conclusion. Yeah, so if you're interested in Silene, then I think you can just type in Silene into Google, maybe add lean/GitHub into it. Then, yeah, again, if you want to learn more, I would welcome you to read this, the reference manual or the very version of it. And yeah, again, like I met lots of people confused about what Silene is. So I would like to again stress that Silene is the primary thing is to figure out how we can use Lean for scientific computing, and the main focus is on like how to do it, how to make it easy to use Lean, and how to make it kind of nicely composable and stuff like that. And proving everything formally correct is not current primary goal. It's written such that like sometimes in the long future we can improve everything. So yeah, I think that's all. I'm happy to answer questions for some time.
Sounds good. Thank you.